Hello everybody, myself Prashant Mukhopadhyay, faculty member Electrical Engineering Department, Greater Kolkata College of Engineering and Management. In the last class, we were discussing about single phase half wave control rectifier or half wave converter with RL load. Now today we'll discuss single phase half wave converter with RL load using freewheeling diode. So in this half wave control rectifier, freewheeling diode is connected in parallel with the load. This diode is described as a commutating diode or flywheel diode or bypass diode. So this diode is commonly described as a commutating diode, as its function is to commutate or transfer load current away from the rectifier whenever the load voltage goes into a reverse state. So this diode serves two main functions. First one, it prevents reversal of load voltage except for small diode voltage drop. And secondly, it transfers the load current away from the main rectifier, thereby allowing all of its thyristors to regain their blocking states. So this is the circuit diagram. So this is the flywheeling diode or freewheel diode. So this is connected across the load. That is, load is RL load. This is the source voltage. This is your thyristor. Okay, so this is voltage drop across thyristor. This is output voltage, and this is the load current. So how it operates? So actually, with diode, thyristor will not be able to conduct beyond 180 degree. Induced voltage in inductance will change its polarity as dIdt changes its sign, and diode, this DF, which is the freewheeling diode, will start conducting as soon as the induced voltage is of sufficient magnitude, thereby enabling the inductance to discharge its stored energy into the resistance. So hereafter 180 degree, the load current will freewheel through the diode, and a reverse voltage will appear across the thyristors, and as a result the power flow from the input takes place only when the thyristor is conducting. And if there is no freewheeling diode, or during the negative portion of the supply voltage, thyristor returns the energy stored in the load inductance to the supply line. With freewheeling diode DF, the freewheeling action takes place, and no power will be returned to the source, and hence the freewheeling diode improves the input power factors. So once again, I'm explaining. This is the circuit where the freewheeling diode is connected across the load. This is RL load. This is the input voltage or supply voltage, that is source voltage, that is Vs equal to Vm sin omega t. This is the thyristors, and it is the voltage across drop across the thyristors. This is load current. Now operation is like this. With diode, thyristor will not be able to conduct beyond 180 degree, and induced voltage in inductance will change its polarity as dIdt changes its sign, and freewheeling diode DF will start conducting as soon as the induced voltage is of sufficient magnitude, and thereby enabling the inductance to discharge its stored energy into the resistance. So after 180 degree, the load current will freewheel through the diode, and reverse voltage will appear across the thyristor. The power flow from the input takes place only when the thyristor is conducting, and if there is no freewheeling diode during the negative portion of the supply voltage, thyristor returns the energy stored in the load inductance to the supply line, And with freewheeling diode, the freewheeling action takes place and no power will be returned to the source. Hence, the freewheeling diode improves the input power factor. So this is the actually waveforms. This is the supply waveform. Okay, source voltage Vs equal to Vm sin omega t. This is the Vm at pi by 2. This is your firing pulse given to the thyristor gate at firing angle alpha. Okay, and this will be your load voltage. Actually, thyristor conduct from alpha to this pi, that is pi equal to T1. So this is your load voltage. Okay, and this is load current. Okay, so we are coming how this say waveform is being generated. This is due to the current. This is your current due to the freewheeling diode. This is the thyristor. This is for the freewheeling diode, and say this will be the entire profile of the load current. This is the voltage across SCR. Actually, this portions. Okay. Then this is the conduction state mode. So voltage drop is almost 0, and again, so it is again fired at. So this is the blocking reverse forward blocking voltage. Okay. Now this is again firing angle. The gate pulse is being fired, and this portion is the voltage across the thyristor. Okay, so this is the model waveform of a single phase half wave converter with RL load using freewheeling diode. Now this all about your discussions about RL load with freewheel diode for a single phase half wave converter. Now we'll extend our discussions. If we extend the load with another voltage source, that is a battery in series with RL load. So in that case, the circuit diagram will be like this. So load circuit consists of a DC source E in addition to this resistance and inductance. SCR will be power best for anode supply voltage greater than the load voltage, that is when the source voltage Vs is greater than this E, so it will be in the forward bias mode. Okay, and if the value of this omega t, so V is equal to Vm sin omega t, so omega t at which the supply voltage increases and becomes equal to the load circuit DC voltage, and can be calculated as this gamma equal to this is the angle, so it is sin inverse E by Vm. For trigger angle alpha less than this gamma, the SCR conducts only for omega t equal to gamma to beta, and for trigger angle or firing angle alpha greater than gamma, the thyristor conduct for omega t equal to alpha to beta. So if we say the output voltage V equal to output load voltage Vm sin omega t, if we say output load voltage for omega t, it will be, this is how you happen when omega t equal to alpha to beta, and output voltage will be equal to the DC source voltage with the load connected with the load E for omega t equal to 0 to alpha, and for omega t equal to beta to 2 pi. Okay, so this will be output voltage will be E, this one, that is for omega t equal to 0 to alpha, and for omega t equal to beta to 2 pi. So load current can be found as this is equal to source voltage Vm sin omega t. This is the drop across this resistance, and this is R L di 0 dt. This is the drop across inductance, and this plus E. Okay, so when alpha is omega t is will be in between alpha to beta, and in that case I0 will be Vm by Z sine omega t minus phi minus E by R plus A e to the power minus t by tau. Okay, so this is the load current here. So actually this is the profile like this. This is your output voltage. Okay, your voltage actually this will be like this, and this is your out load current. This will be like this. Okay, so this is actually conduction angle. Okay, delta. This is firing angle. This is the total conduction angle. It is thyristor conduction angle, and this is your total conduction period. So this is load current. Okay, and if we calculate this current like this, so output current will be this, and it will be 0 at omega t equal to alpha. In that case, this value A, this A is the constant that can be found out, and as a result, this will be the output or load current. This extinction angle beta, extinction angle can be calculated at I is equal to Vm, I is equal to 0, and if you put this equal to 0 or at omega t equal to beta, so this will extinction angle will be found. So average DC voltage in that case will be 1 by 2 pi 0 to alpha. This expression you can find out from this 0 to 2 pi time period. This is actually the value. Okay, and conduction angle for thyristor delta will be beta minus alpha, and note that this output DC voltage that is equal to E plus I naught R, and RMS output voltage can be calculated by using this expression. So this is the expression. Okay, and for L equal to 0 Henry, beta equal to pi minus gamma, the average load current can be given as like this. Okay, and RMS load current for L equal to 0 Henry can be given as this, power of 1 by twice pi integral alpha to beta Vm sin omega t minus E by R whole square to d omega t, and from that we will get this RMS value of the load current, and power delivered will be equal to PDC equal to I over square R plus I naught E, and the input power will be like this. Okay, so this is actually about the RLE load. It in details, if we take this circuit and the total voltage waveforms will be like this. This is the source voltage waveform. This is gate pulse for firing purpose. This is the output voltage waveform. This is source current or output or load current. This is like, and this is the voltage across the thyristor. Okay, so this will be like this. So this is actually the, if we take all the waveform of source voltage, gate pulse, output voltage, source current or output current, and voltage across this thyristor, if we taken into consideration, so waveform will be like this. For the circuit is like this, most laboratory I am telling you. So this is your about the single phase half wave converter circuit with RLE load and its waveform. We have discussed the details of its operation and its calculations. This of different actually this is output voltage, then output current or load current, then different conditions, then RMS value of DC output, then RMS value of the load current, and then from we have discussed, we have calculated the DC power delivered to the load, and then input power factor is like this. So with this we have say discussed all about the different waveforms and that's all about RLE load connect. So far we have discussed about the single phase half wave converters or single phase half wave control rectifiers, and we have discussed this half wave converters with resistive load, with resistive inductive load, with resistive inductive load along using a freewheeling diode, and also we have discussed about this single phase control rectifier with RLE load. Okay, and in every discussions we have discussed the circuit, the how this circuit operates, and what would be the ultimate waveform, that is actually the source voltage waveform, when the gate pulse is given, how the waveform of the thyristor voltage, and we have discussed about the what should be how the nature of the waveforms of the output voltage and the output current, and how this waveform is getting changed along with the change of variation of the load from resistive to resistive inductive, and then how the stored energy across this inductive load is being say dissipated or is being circulated to the using freewheeling diode. So by just giving blocking this say the inductive load to get back to the source, or rather it will be flowing through the load itself, and in that case how the waveform will be changed, and that also we have discussed. And lastly we have discussed the waveform, actually operations of the single phase controlled half wave control rectifier along with RLE load, and with this loads how this the waveform, actually the source voltage waveform, say output voltage waveform, output current, and the thyristor voltage waveform will be. We have discussed. Not only that, we have discussed that different say parameters, that is current, voltage, that is actually we have discussed about the load current, its different positions with the value of the omega t, and how this waveform is being generated with and supporting this in support with this equations of say output voltage, output current, thyristor voltage, etc. So that is discussed, and in totality how the power is delivered to the load, and what is its amount, and what should be the input power factors, and that also we have discussed in this single phase half wave control rectifiers with different types of loads, and with variations of these loads, how the different waveforms has been being generated and waveforms has been modified or changed, that we have discussed. Now we'll start a new topic, that is single phase full wave rectifier. Actually single phase full wave rectifiers of different types, it is center tap and bridge rectifiers, whatever it is. We will first start with center tap. Say let us discuss this circuit diagram. So this is a full wave controlled center tap rectifier circuit with resistive load. Okay. See, for this is center tap. Actually, this is the in source voltage, and this is actually source voltage. This center tap from here. Okay. So this is actually the basic arrangement of a single phase center tap control rectifier with resistive load. So phase control of both the positive and negative halves of the AC supply actually is now possible because two thyristors are used here, thyristor 1 and thyristor 2. This is got say positive half, and this is for the negative half of the supply. So this and as a result, it will increase in the DC voltage and reducing the ripple compared to those of the half wave rectifiers so far we have discussed. So see, this is actually for the positive half. This is again for the negative half actually. So this is a resistive load. This is resistor 1, this is resistor 2, and this is the load current. Okay, so let us discuss its waveform. Waveform will be like this. This is say source voltage waveform. So actually 0 to pi is the positive half, and pi to pi negative half. Again pi to pi to 3 pi is the positive, and so on. So and this is the maximum value of the source voltage, so which is happening at omega t equal to pi by 2. Now this is the output voltage waveforms. Basically this is the firing angle. This is the load voltage, or you can say the output voltage say across appear across the load. And of course this is the load current. Definitely it will be since the load voltage is divided by the resistor the load, so current magnitude will be little bit reduced, and that depends on the value of the resistor. But the waveform will be same like this because it is a resistive load. Okay, this is firing angle. Clear? Now of course this is the current through the, since we are during the positive half, so this is the thyristor 1 or SCR 1 is getting fired. So as a result, this will be the current through the thyristor 1 or SCR 1. And for the negative half, this thyristor will be not charged, and in that case thyristor 2 will be as in center tap. So thyristor 2 will be fired, and this will be the load current or thyristor current is actually through the thyristor 2. And again for this positive half, so this will be again the thyristor 1. Okay, so if we say connect these two, so this will be the source current, or this is the load current actually. This will be like this. Okay, this will be like this. This is the load current, and of course this is your voltage across the SCRs. Okay, so SCR 1, SCR 2 voltage and current. Clear? So actually this is actually like this. So so this is full wave center tap control rectifier with resistive load and waveforms. Now during the operations like this, during positive half cycle of the input voltage, thyristor 1 is forward biased, and if we apply gate signal at alpha, thyristor 1 will turns on, and the output voltage follows the input voltage, and load current also I0 equal to V0 by R has the same waveform as the load voltage, so that we have discussed. And at phi, when the current through SCR1 becomes 0, it turns off naturally, and during the negative half cycle, SCR2 is forward biased, and SCR2 is fired at angle pi plus alpha. That is shown here. This is actually pi, and this is pi plus alpha. It is shown here, thyristor 2. Okay. So the output voltage again follows the input voltage, and the current through SCR2 becomes 0 at 2 pi and turns on, and it turns off. See, at current is 0 at 2 pi. Yeah, actually this is 2 pi plus alpha. So actual case is that in that again after 2 pi plus alpha, SCR1 is again fired, and SCR2 again at 3 pi plus alpha. So in this way, the cycle repeats. So this is the resulting voltage and current waveform, as I say, as it is shown here. I told you this is like this. Okay. So so that's all about this full. See, this way it is having the full wave. Okay, like this. This is full wave. Okay, so actual case is like this, and if we now find out the average value of the load voltage will be, this will be like this. This is the average value of the load voltage is twice that given by this equation. So actually, V output average is equal to Vm 1 plus cos alpha by 2 pi into 2. That will ultimately it will be Vm by pi into 1 plus cos alpha. And RMS value of the current will be like this. So IR is I into 1 minus alpha by pi plus sine 2 alpha by 2 pi whole root over of this, actually to the power half. So, and this can be calculated like this. This is the output voltage waveform. So if you go to the waveform, so we'll calculate the average value of the output will be like this: 1 by twice pi to the integration alpha to pi root over 2b sine omega t d omega t, and this will be like this. If you taken it back 0 to alpha to pi, so it will be sine omega t d omega t. Okay, so 1 by 2 pi to like this. Actually, so this is output average Vm by pi 1 into cos alpha, and output current, average output current will be this. This will be like this. So actual the RMS value for the output voltage and current given will be like this. Okay, RMS value root mean square value. Actually, first square, then this is square, then mean, then root. Okay, so it will come to this value. RMS output, RMS value of the RMS output voltage, and current will be like this. Okay, so this will be also like this. So the difference is that it is the maximum value of the voltage, it is the maximum value of the current. The average and the RMS value of the SCR are given like this. This is for average value of the thyristors. Okay, 1 by 2 h by d alpha to pi to v by r sin omega t d omega t, and then ultimately it will be like this. And this is RMS value. Okay, so output current is given, actually output power, not output current. Output power is given by this actually. So this is P0 I0 this like this. So input power supply power factor will be like this. So that we have to discuss in our whenever we are talking about a single phase say half wave synchronous converter also. So we have found the output power and then input power factor. So that's all about this input output power and input power factor. So actually, so this is the first case of center tap single phase full wave converter with resistive load. Now we have discussed this with this is the center tap one with two thyristor. This is for the positive half, this is for the negative half, and this is the resistive load. Okay, this is the waveform. This is the source voltage waveform. This is output voltage waveform. Okay, this is actually output voltage waveform. This is actually source current or how to say current waveform, and it's all about the discussions and